welcome you to this lecture of microscale transport process. What we have been discussing was dielectrophoresis. We briefly introduced, or we started the introduction of this dielectrophoresis in the last class. What we mentioned in the last class, that we have this Navier-Stokes equation here. Here we have this Navier-Stokes equation, where we have this body force term arising from this electric field, which has I, j and k component. What we mentioned in the last class, we tried to describe something called a polarization, where we mentioned that a small particle such as a biological cell occupy region omega in space centered around the position vector r0 having electrical charge density rho E L. So, it will have a force integration dr, basically this body force term in the Navier-Stokes equation, this will take the shape F E L is equal to integration for all. We are talking about a region omega, not just a point, and for this region omega we had that integration dr rho E L E, this quantity that is integrated over the entire region. By that what we mean is, we have a particle, we have a small particle, and we in this particle we have charges present, plus minus, these charges are present, and we have an, if there is a net charge, then this would be reflected there. Now, these what we are trying to find out here is, we are integrating rho E L E, this product, for this entire region omega. So, for various positions here, and we are integrating this product, that is what it means. So, this is the electrical, this is the force component, and the ith component of this force was given last time as this. This was given as a ith component of the force for DEP, where r naught plus r is a general position inside the particle. That means, I have a reference point. From there, I have located this particle at a distance, located this particle at a position vector r0, okay. And then we have within around this particle we have constructed a volume or a region omega. So, that region is defined as these various points within this region is referred as r0 plus r. So, r0 plus r is a general position inside the particle. So, this is the force term in that case. Now, what we did in the last class was, we have expanded this using Taylor series, this that E basically the electric field, that term we have expanded using Taylor series, and only we have taken the first order terms. We have not taken the terms beyond first order, and since it is a multivariable system, so we have we have I, j and k involved. So, we have basically this is a Taylor series expansion in a multivariable sense. Then we have written this product as Q into EIR0, and this product of this and this, that we have written as Pj del j EIR0. So, this is one term and this is another term. This is how we have written this ith component of the force arising from this electric field. Now, we said what is Q? Q is basically integration of this dr rho E L r0 plus r, and this is referred as charge of particle. On the other hand, this P, which is basically referred as electric dipole moment of particle, that is this quantity dr rho E L r0 plus r into r. So, this is called electric dipole moment, and this Q is charge of particle. Anyway, these are immediate result of this expansion of this expression. Now, what we said is, in case of an in case of what we had done before, say electroosmosis and other places, there we have this Q present, there we have a Q, there we have this Q present, there we have this EI present, and they contributed to the force. But in this case, we at the very outset we said Q is equal to 0. So, this term is 0. However, we said that derivative of this E, that means del of E, that is non-zero. That means the electric field is non-uniform. So, because of this non-uniform electric field and because of this non-zero Pj, this term features. So, we have a force. So, what this means is there is a particle. The net charge on this particle is 0, because the number of pluses that you have and number of minuses that you have, they sum up to be 0. So, the net charge on this particle is 0, but still some force is exerted on this particle by imposing a non-uniform electric field. That is what we are talking about, and this force we are referring as dielectric force, and the definition of this force is P dot delta E, where P is this quantity, electric dipole moment of particle. So, this is what we have done, we have briefly introduced in the last class. All right. So, now if we try to write this, if we try to now before we get into this further, let me do one thing. Let me just define this dipole moment density. This is something which is there in the literature. Dipole moment density P of R 0. Let me put it, this is a capital P. To differentiate this, we had a small p here, which is electric dipole moment of particles. So, this is a small p. To differentiate this, this is a small p. So, we have to differentiate this, we have capital P here. This is defined as limit volume of omega star tending to 0, 1 divided by volume of omega star integration over omega star dr rho El R 0 plus R into R. So, this quantity is, so this is referred as dipole moment density. Now, I said that we need to establish a non-uniform electric field, such that this del of E is non-zero, gradient of E is non-zero. So, this type of field you can establish by having a planar electrode on one hand, this is a planar electrode, and a point electrode on the other side. This is a point electrode and this is a planar electrode. So, you have, this is the plus and this is the minus. Okay. So, you will be pulling charges here and you will be having. So, if somebody wants to draw the electric field, you can see that automatically it would be non-uniform in a sense that these would be the, this is how the fields will be located. Or I do not want to put the arrow here, but at least think of the. So, this is how the field, this is how the field is located. All right. So, what would have been an uniform field is that you have one electrode here, another electrode here, which are both are of same size, and you have this electric field. This is known as this is uniform electric field. Here you have a non-uniform electric field. Now, suppose you have a dielectric sphere present here. In this non-uniform electric field, you have put a dielectric sphere or dielectric particle, okay, which has certain epsa. All right. So, we call this epsa of particle, and on top of that you have a medium in which this particle is suspended, and let us call this as epsa fluid. And we note here that because of this non-uniform nature of the electric field, the concentration of electric or the highest density of electric field lines, is around this location. So, on the left of the particle. that is the place where the field density, these electric field lines are most concentrated. So, this is the region of strong E field, strong electric field is in this region. You remember those streamlines getting converged, and the place where the streamlines are coming close to each other, that is the place you have the highest velocity and things like that. So, this, I mean, you can think in that context as well. So, here you have the electric field lines which are coming, electric field lines which are concentrated near this on the left hand side. So, the region of strong E field, strong electric field is on the left hand side. So, there is one issue here, either it could be that the EFSA particle, either the EFSA particle is more than EFSA fluid, or the other possibility could be that EFSA particle is less than EFSA fluid. The dielectric constant that for a particle and a fluid, they can be little, they can be different, one can be higher, one can be larger than the other. All right. Now, if the EFSA particle is more, if EFSA particle is more, in that case you can expect more polarization charges at the surface. If under this condition the EFSA particle is greater than EFSA fluid, there would be more polarization charges on the particle. What does that mean? There would be induced polarization that we have been talking about, this electric dipole moment, etc. So, there would be charges on the particle, net charge is 0, but on the surface there would be plus charges and minus charges. Think of what happens in a capacitor. I mean, if you have two electrodes and if you have dielectric, say a dielectric particle present, what you will find is that, say, plus and minus, this dielectric particle will align itself, the charges will align itself such that it remains this way. Another dielectric particle will align again here, plus and minus, another would align here. So, originally when the voltage was not applied, when the electric field was not applied, that time you have the you have these oriented in a random manner. All right. But now, if you impose an electric field, you will see that the charges, they get aligned in the direction of the electric field. That is how it works. All right. Now, these charges I am referring as the surface the charges that is available on the particle. The net charge is 0. Okay. Now, if the EFSA particle is more than EFSA fluid, under this condition, you will find that more number of more charges are available on the surface of this particle, and in that case this particle will be drawn towards the region of strong electric field. Why will it be drawn? I mean, if this electric field would have been uniform, if this electric field would have been uniform, as is the case here, in this case just the particle will align itself, okay, and sit there. So, at the end of the day, you will find all these particles, they are aligned, plus minus plus minus plus minus neatly, no movement of the particle, nothing. That is what we understand. Now, here you have a non-uniform electric field. So, if the particle tends to align this way, it would be extremely difficult for the particle to retain the equilibrium. So, the only way the particle can align itself is by moving towards this, and since this electric field is non-uniform, so it will keep moving towards the left hand side, such that it can establish this kind of structure. All right. If instead of this spherical electrode, if I would have had a planar electrode, particle would have aligned, this particle would have just simply aligned itself such that the charges are corresponding, all the negative charges would have been in this direction, and all the positive charges would have been, or I mean it will be that way, but the particle will not move. I mean, depending on what is the sign of this electrode, it will have some particular charge will be on this side, some other charge will be on this side, but the particle will sit there. All the charges will be arranged, they will be aligned that way. But here in this case, you have a non-uniform electric field, not a planar electrode, but a point electrode. And because of this non-uniform electric field, this particle this particle does not have any way to go. Only way it can, if it tends to satisfy this sort of condition, only way it can satisfy itself is by it will keep moving towards the left hand side, and more it moves, again it is non-uniform that way. So, the only way it can restore the only way it can what it can do at this point is it will keep moving on the left hand side. Now, think of the case when f sub particle is less than f sub fluid, that means this particle is less polarized and the fluid in which the particle is suspended, that is more polarized. In that case, the surface charges on the fluid, that would be more than the particle, because particle will have less charges, the fluid will have more charges. Okay. So, in that case it would be easier for the fluid to move towards this direction than with reference to the particle, or in other words we can say the particle will be pushed towards this direction. So, when f sub particle is greater than f sub fluid, the particle, so I should write this down clearly, when f sub particle is greater than f sub fluid, then the particle will be pulled to the region of stronger electric field, that means to left. And when this is the case, then particle will be pushed to right. So, what you basically do here is you are having to you are creating a non-uniform electric field, and by imposing a non-uniform electric field you are pulling some particles and not pulling some other particles depending on the dielectric constant of that particle. So, that is what is the bottom line, what we discussed so far. Now, the very common way of utilizing this process is there is something called a Dep trap. Dep trap means you have basically you have a situation like this where the fluid is flowing. So, suppose you have a channel, this is one wall of the channel and the opposite wall is the point, there is this point electrode. One wall you have planar electrode, another wall as point electrode, and you have particles, different particles, okay, they are flowing through this flowing through this region. So, depending on the FSA of the particle, you expect some particle will be pulled towards the point electrode and some particle will be pushed away from the point electrode. Okay. So, there is one thing could be that you can use this channel in a filled flow fractionation mode. You are already familiar with what filled flow fractionation means. That means you have you are collecting the sample, but by the time it comes out, this would be, since you have a parabolic velocity profile. So, near the wall the velocity would be 0 and away from the wall near the central part of the channel the velocity would be highest. So, the central part of the channel will come out first and the layer that is next to the wall, that is taking the longest time, that is taking the most time to reach the outlet. So, if you create a fractogram, that means if you have a detector connected at the outlet and if you collect, so it will continuously, it will measure the average means average over this cross section, whatever it receives with time. So, in that case you will see peaks, one peak arising from the layer that is arriving first, the central one, then the one that is coming later, and the one that is placed next to the wall that will come at the end. So, you will see peaks. Now, if you can align particles depending on their dielectric property, if you can align the particles on within this channel at various locations, then you can at the outlet, when you receive it at the outlet, you can detect them and against a pre-calibration you can find out for an unknown sample what all particles you have. That is one way of doing it, using field flow, using this DEP in a field flow fractionation mode, which has been which researchers have already studied. The other possibility is the DEP trap that I said, that you trap the particle. I mean, suppose so many particles are flowing through this, but some particles satisfy this EPSA, and those particles will be trapped next to the electrode. Okay, so once the process is done, suppose you have a sample, a slug, and you flow the slug through this place, and within the slug whatever particle you have that satisfy this condition, you trap them next to the point electrode. So this could be another way of looking at it, and this is referred as DEP trap. Now to have this DEP trap working, so what is this DEP trap? If I try to articulate it in a sentence, it would be that the dielectric force can be used to trap dielectric particles suspended in microfluidic channel. Now, you say that these particles will be trapped when particles will be trapped by the electrode if mod of FDEP. FDEP is that P dot delta E that we already described. These has to be greater than the drag force. Your immediate response would be that since we have a non-uniform field here, or the way it operates here, I mean, why we don't have an angle or anything? I mean, can we just equate FDEP with F drag? I mean, that would be your immediate response. My belief is that this is a limiting situation that they are talking about, the limiting situation next to the electrode. So this is how probably this can be reasoned. I mean, I would probably like to have your views also on how it should be done, but FDEP we have some idea P dot delta E, and F drag will come from that Stokes law. I mean, that is perfectly applicable in this case. So this inequality basically shows the limit of it. I mean, ideally there should be an angle involved. Now, Stokes law says F drag is equal to 6 pi eta a v, v at a position, v at r. What are these properties? 6 pi is 22/7, a constant. Eta is the viscosity of the fluid, right, and a is the radius of the particle, and v is the velocity of the particle. So this is the Stokes law. This we already have talked about. So if you want to write, I mean, probably we need to note here a is equal to radius of dielectric particle trapped in position r, and what is v? V is, if this direction is x and if this is z, we are talking about a point a point electrode and a planar electrode. So this is the point electrode, this is the planar electrode, and this direction is x, this direction is z. If that is so, that means the flow is taking place in this direction, and this is the point electrode and this is the planar electrode, and particles would be trapped near the point electrode. That is the idea. Then what would be V in that case? V would be given as V x as a function of z E x hat. I mean, we are ignoring this. So we have y is in perpendicular to the paper, and that part we are taking that it is indifferent. So V is equal to V x z E x hat, and then these V x z, how will you write this V x z for a channel? Let me write this. I mean, what I got this as an expression. I think they should be. You can verify it yourself later. Six into 1 minus z by h. H is the aperture of the channel, right? So 1 minus z by h into z by h V 0. V 0 is the average velocity E x hat. This is that same expression we had, you remember, 2 V 0 into 1 minus r by r whole square for a laminar flow through a channel in circular channel. So, I think if you go for a laminar flow through a rectangular channel, which happens to be a microfluidic channel, you would get this expression. Probably you should look into this. Now, here one catch is there. You are assuming this to be an infinite parallel plate. That means H is much less than W. Infinite, this term itself is relative. That means, if this W is 1 centimeter and if this H is 1 micrometer, then probably you can still consider that to be infinite. I mean, it is that way. So, it is, as long as this aperture is much smaller than the width of this perpendicular to the paper, whatever we have, this, as long as this H is much smaller than W, you can assume that these plates are infinite parallel plate, and of course, you need to have the velocity field fully developed in this direction, that is there. Now, what you are doing in this case here is that we do not have any W in this expression for V. So, this is simply the velocity field. I mean, we should be happy with it. There would be formation of Debye layer next to the particle. That is a possibility. You remember that when we talked about electrophoresis, we said that this Debye layer is basically instrumental in pulling. So, similar Debye layer around the particle could be, there is a possibility of formation of this Debye layer. However, that possibility would be gone if somebody uses an AC electric field. That means alternating current electric field, and that is very common. In fact, if you look into any advanced literature on DEP, you will find that they will start with these AC electric field altogether. But I thought it would be wise to first build it from scratch, and then probably point out which all parameters would be affected if there is an AC electric field. So, if somebody employs an AC electric field, then probably the formation of Debye layer around the particle, that would not be important. Okay. So, that is the situation here. Now, how would you, this is the F drag. So, we have already figured out how F drag would be 6 phi eta A into V, and that V would be replaced by this quantity. So, this drag part is simple, the right hand side part of this inequality is simple, but for left hand side you need to find out F DEP. Now, you may say, I mean, what are we trying to do? I mean, DEP trap I understand the inequality, but what are we trying to solve by putting this writing this drag force? Our objective is to find out what should be the V naught, what should be the electric field such that you can trap a particle of certain epsilon. So, what should be that expression? How would you? So, what should be? Suppose somebody gives you the okay. I want to trap particle of this dielectric constant of this size. Okay, A is given, F size given, and now I have this much of electric field at my disposal. Tell me what should be the V naught such that I can trap the particle, because if you are beyond that V naught, then you cannot trap the particle, it will simply flow away. So, that is probably something which we are trying to establish, but by doing this what we would have is we would have some clarification on how these DEP force etc. are handled. That is probably the objective. Now, F drag part, the right hand side part of the inequality already we found out. Now, F DEP part, which is nothing but P dot delta E, we have already discussed this, right. We have already established that this force is P dot delta E. So, now we have to focus on this part, how this relates to the F drag and how we can find out what should be the V naught. Now, we said that it is an inhomogeneous electric field. Okay. Now, how will you create an inhomogeneous electric field? Before we get into this inhomogeneous electric field, what we do here is first let us find out an expression for P. Delta E is one thing, we will find out how we handle this delta E. I mean basically look at this, we have F DEP that is equal to P dot delta E, that is what we said. Now, we have two issues in hand here, one is this P, another is E. Now, how will you find E for this case? Point electrode and planar electrode, how will you find E? That is one issue. The other issue is how to find P. So, these are the two things you need to resolve, then only you can find out what is FDEP and then you can equate it with F drag to find out what should be V naught such that you can trap the particle. Now, before we get into this before we get into finding what is P, let me point out a couple of things here. Suppose we have an uniform electric field, okay, and we have a particle. How would we have done the polarization? The unperturbed electric field lines, they would be something like this, right. These are all plus, these are all minus. So, these would be the field lines, and near the particle there would be some twist like this. All right. Now, how would you find P in this case? How do you first of all let us find out how you can solve this case of unperturbed electric field line. Now, unperturbed field lines is this, there was no sphere, it is all straight line, but because of this particle there would be some twist here. How will you find out what governs this twist? That is something which is important here. Now, here we can do one thing is that you need to first of all I mentioned here that the electric field polarizes the dielectric sphere. The electric field polarizes the dielectric sphere, PHE, dielectric sphere, I write this as sphere of radius A. Now, radius A and dielectric constant epsilon 2. Now, there will be distortion of electric field lines and if somebody wants to theorize or somebody wants to simulate by theory there were this distortion of electric field lines, what he has to note here is that phi, the potential in r theta coordinate, here we have one coordinate system which was we said that this is x, this direction is x, this direction is z, that is what we had originally, right. Instead of that we have another one which is r theta coordinate, this angle. I mean, instead of a Cartesian we can go to a go to cylindrical or polar system. So, if we go to this phi r theta, this coordinate system, here we have to note that this would be equal to phi 1 r theta for r less than a or r greater than a, we are calling it, and phi 2 r theta for r less than a. What is a? A is the radius of the particle. So, you have a potential, you have a phi inside this particle, you have a phi outside the particle. So, this is the phi r theta. So, you have one phi 1 function, you have one phi 2, all right. Now, what you need to finally solve here to find this p, what you need to solve here is this del square phi r, that is equal to 0. This is the governing equation for the fluid and sphere. This is the governing equation that needs to be solved. However, there are boundary conditions. The boundary conditions are phi 2 0 theta, phi 2 is inside the sphere, inside the particle, phi 2 0 theta is finite, that is one thing. Other is continuity, which is important. Phi 1 a theta, that is equal to phi 2 a theta, that means where at the end the place where the sphere ends and the fluid begins, there has to be a continuity in phi, their derivative. You need a continuity there as well. You need a continuity there as well, and after all these phi has to be related to the electric field lines, because originally you have imposed a E there, right. You have imposed some electric field E, and how is this E and phi related? What is phi and what is E? You remember E, what was phi is the potential and E is the electric field. How we defined this? We said that if del cross E is equal to 0, then E is equal to minus delta phi, right. This is the definition. At the very outset we said this. You go through your earlier notes, you will see. I mean, in fact, we compared this with our velocity field and existence of potential function, that exactly it is in a similar manner. I mean, we discussed this before, how we obtained this in connection with electric double layer. We discussed this in detail. So, go back to the notes. So, this is how it is related, and this E you have imposed, okay, and E is equal to minus delta phi. So, this has to be satisfied. Now, how will you satisfy it? Because you are talking about some r theta coordinate here and E is imposed in this direction. So, if you want to do that, you should be writing it as, so what you should be writing here is phi 1 r theta, that is that tends to minus E naught r cos theta as r tends to infinity. That means, you have what is E? E is basically minus del phi del r, all right. So, you have to write this at far away from the origin, you will not have any of these twists felt. So, if you write it that way, so you have to write it phi 1 r theta is equal to minus E naught r cos theta. So, this is that. So, far away from this particle, it would be simple unperturbed electric field lines. So, that is what this boundary condition states. So, now if you have these boundary conditions in place and if you solve these governing equation, and with these boundary conditions in place, okay, and then what was P originally? I mean, I am not going to talk about how the solution is done. I will give the final form here. At least you want you to appreciate what all steps we have gone through. This is the electric dipole moment here. And you know how this rho EL term, is related to phi, that we have already discussed in connection with electric double layer. So, if you solve this equation and finally get to that P, what you would end up with is P is equal to P near R0, P near R0. I will get back to that. 4 pi, let me write the expression first. This is the expression that you get in that case. If you solve that equation, that's the idea, solving that governing equation with these boundary conditions, you end up with this expression. And what you write here is if Dep, mind it, the trapping will take place, the trapping will take place close to the we are calling it spherical electrode, that point electrode, we call it spherical electrode, close to the spherical electrode, that means the R value that you work with is much less than H. Okay. R value that you work with is much less than H. So, what you write here, if Dep at R0, that is equal to P of R0 dot delta into E0 R0 plus there are other higher order terms that you are not considering. What was your basically this f Dep R0 here there should be some other higher order terms, because what you are doing here is this, you are writing this as E0 R0, this E0 is with reference to unperturbed electric field, all right. So, basically this was the E0 term. You remember this was the unperturbed electric field line. Now, here if you cannot ideally, I do not think you can write this in terms of E0. So, there should be other higher order terms which you are not considering in this process. So, you are only focusing on these P r 0 dot delta E 0 r 0, that is what you are saying here, and then you are bringing in these expression for P inside. So, what you are getting in that case is 4 pi epsa 1 epsa 2 minus epsa 1 divided by epsa 2 plus 2 epsa 1. There is a name given to this factor A cube, and then you have E 0 r 0 dot delta E 0 r 0. Okay. Now, there is an identity here to solve this equation further. There is an identity which needs to be utilized. That identity is that 2 E dot delta E is equal to delta of E square. Have you seen this identity? This identity is possible because this is based on I mean let me point out that this, what is this delta of E square? Delta of E square is equal to del of I E j E j, that is what it means. Okay. And on the other hand, the left hand side, you can equate this to the left hand side only if you have del cross E is equal to 0. What this means is del of I E j is equal to del of j E I. If del cross E is equal to 0, you know how a cross product of a vector is, and that means that this has to be satisfied. Okay. And if this is satisfied, then only you can equate the left hand side with the right hand side. Okay, because right hand side is basically this quantity. So, other cross terms can be taken off. I mean, if you have this, this is for I is not equal to j, this thing is for I is not equal to j. So, this is an identity, and that identity needs to be used here in this case to come up with this final expression for f d e p, which appears like this: f d e p at r 0, that is equal to 2 pi epsa 1 epsa 2 minus epsa 1 divided by epsa 2 plus 2 epsa 1 A cube delta of E naught r 0 square. Okay. So, this is something which you have for f d e p. All right. Now, you have to find out some expression for this electric field in this case. What ideally you should be doing is this electric field, think of it, you have a planar electrode and a point electrode. This is simulated by considering, so here it is phi is equal to plus delta v, okay, and here phi is equal to 0. Instead of that, what you do is you do not consider this planar electrode, instead you consider a mirror electrode. So, if this is at z is equal to 0, if this is at z is equal to h, this is at z is equal to 2 h, and here it is minus of delta v. It is plus of delta v, here it is minus of delta v, and think and look at the electric field lines. How would they be operating in this case? They would be like this. And this is same as, I mean, whether you consider this a mirror electrode, whether you consider a mirror electrode here, the effect would be same as considering a planar electrode here. So, instead of considering a planar electrode, you can work with 2 point electrodes, 2 h distance apart, and phi is equal to plus delta v here and phi is equal to minus delta v here. So, that is also another possibility, and using this method you can find out how these. So, this is a concept of inhomogeneous electric field, and in that case you can have the phi to be written as r 0 divided by r delta v minus r 0 divided by r minus 2 h E z. Into delta v. So, this is the definition of phi r in this case. Okay. You can check it yourself. Say at r is equal to h E z, r is equal to h E z, that means where? This plane. At r is equal to h E z, check what you have for phi. This should be equal to 0. So, this is what the phi that you would be working with. Okay. So, from this you can get some idea of what should be the electric field, what should be the electric field here, and then impose that electric field in this expression and take the derivative of it, and then you can get the final expression for f dep. The idea is to equate this f dep with our original expression of this inequality f dep with f drag and come up with the expression for V 0. So, what we have done is, first we have used for unperturbed electric field. So, if I quickly summarize, we have used, this is the original expression for dep p dot delta E, and we stuck to this, we remained true to this. Only thing is, we said that if there is a particle inside an unperturbed electric field was E 0, that means particle was not there, just the electric field was there, value E 0, and we said that is the case at infinity. That is the case at infinity, and we solved. We have defined two sets, phi 1 and phi 2, for the two, one is within the sphere and the other is outside the sphere, the potential, and this is the governing equation that was solved. I mean, we did not solve, I just said that these are the steps that has been solved by the researchers to come up with an expression for P, which is here, and then we put this expression into this. However, here instead of the electric field we use the unperturbed electric field, but by that we made an approximation. We should have, if you expand in Taylor series form, then this should have been expanded. That was not considered, and used the unperturbed electric field and continued that way. And there was this identity that was utilized. This identity could be utilized since this del cross E is equal to 0, and that identity has gone in to find this E dot delta E. Instead of this, this allowed us to write this as delta of this thing square, and then we are going to obtain the potential, we are going to put this electric field here and take the derivative of it to come up with the expression for f dep. This we will equate with f drag to find out what should be the V naught we can tolerate. So, that is what the essence of this. So, I will continue with this in the next class. That is all I have for today.